Hi everyone, my name is Rui,
And I am Yuval.
and this is our project about music genre classification.
Well, our project is about music classification. We can think about it useful when we hear song at Spotify, and Spotify suggests the next song that we would like to hear. The music classification is a multi-layer machine learning problem. We use the database name GTVan, and we use the model Distill-Hubert. And our main part of the project is about using augmentation and seeing how it changing the result.
So the problem itself we are trying to tackle here is the problem of music classification, which is different from the problem which we've talked about in the lectures and tutorials of image classification, which is derived from the fact that when we're looking at the song, we can deduct the genre of the song by looking only at a fraction of the song itself, whereas when we're looking at a picture, we cannot deduct the type of picture which we are looking at, only looking at a fraction of it simultaneously for each picture. Some pictures we cannot do that. In a song, also, we might have multiple correct answers, like multiple genres. In a picture, it's less likely so. And lastly, in image processing, we are focused about object recognition, whereas in music genres, we are looking only on the genre itself.
So let's talk about the model that we use. We use a pre-tuned model named Distill-Hubert. It's a distillation model of the Hubert, a self-supervised model. The distillation based on a teacher and student framework. The model consists of is very complicated and consists an CNN encoder, a few mask area, attention dropout. Even that it is a distillation model, it still has something like 260
Thousand parameters.
thousand parameters. The Hubert model is pre-tuned on a large language model database named LibriSpeech. It's not a music database, and we transform his knowledge to use a music genre classification.
Yes, and the GTSAN database, which we've used on the Distill-Hubert model, which Yuval described, consists of 10 different genres of songs, which each contains 100 tracks, so 1,000 songs overall. And each song is about 22,050 hertz. It's mono 16-bit audio files in one format. We've trained our model itself on about 40% of the data, which is about 40 songs per category, and we use the validation set of about 10%. So a bit less than the regular amount which we would like to use on a project like that. The genres which the model itself contains are described here below, for example, blues, classical, country, and so on.
So as we said before, the main part of the project is the augmentation of the song. We use three different kinds of augmentation. We use the white noise, adding about 5% of the audio amplitude, a white noise. We use a pitch shifting, which means we increase or decrease the main frequency of the audio by about 5%. And we use a band stop filter, which delete 20% of the bandwidth at random central frequency.
So looking at the results which we've received, we can see that there are four sections. The first section is about the regular model which we've used. The second section is about the white noise added to the main model itself. The third section looks at the main model with pitch shift, and the last is the base model with bandpass filter. So, considering the point which I've described above, we've looked at a very little data. So the phenomenon which we see here in the entire data pre-processing and training is overtraining. So considering the data without the augmentation at all, we can see that the graph of the training set is basically zero when we're looking. So the test set stays the same, so it doesn't learn much after it finishes learning the trained data. The same happened with the white noise, so we can see that the white noise performs a bit poorly than the data itself without any augmentation, which was predictable considering this section. Moreover, looking at the bandstop filter, we can see that it performs a bit better than the white noise, but again, a bit more poorly than the original dataset, which is again predictable considering the data which we've looked at. And lastly, when looking at the bandstop filter, we can see that it performs about the same as the original data, which also was predictable considering the data which we've used. In conclusion, we can see that the results which we received performs quite well considering the data which we've used, and we think that we can derive a lot of further work on the project itself using the results which we've received.
Thank you very much. Any question?